For two matrices A and B of the type m by n, the following statements are equivalent. First, A is row column equivalent to B. Second, there exists a non-singular matrix P of order m and non-singular matrix Q of order n such that B is equal to PAQ, where it is pre-multiplied by A and it is post-multiplied by A. Third is, there exists a matrix C such that A is row equivalent to C and C is column equivalent to B. Let's start with the proof. First, we move from first to the second part. What is the first part? It is given that suppose A is row equivalent to B. That means B is obtained from A by applying row and column operations in some order. Let's separate the row operations and column operations by keeping their respective order the same. Suppose that corresponds to the pre-multiplication. Pre-multiplication always corresponds to the row operations by the elementary row matrices. Let's say E1, E2, E3 up to ER in order. And by post multiplication by the elementary column matrices, and let those column matrices be F1, F2, F3 up to so on Fs respectively, right? So thus B is equal to, now B is obtained from A by applying the row column operations. So B is equal to, that is ER multiplied with number of matrices, and we get at here E3, E2, E1 with A, right? And post multiplication of the matrices, we have separated the row and column operations, right, by keeping their respective orders. And now the post multiplication by the product of the column matrices F1, F2, F3 so on up to Fs. Let me name this P. Let me name this Q. Now the nature of the elementary matrices is non-singular, and because P is taken to be the product of all these matrices E1, E2 up to ER, so P is also non-singular. And because Q is taken to be the product of all these elementary matrices F1, F2, F3, and because these are non-singular in nature, so Q is also non-singular. So writing this as P, A and this as Q, where P is a product of ER up to E3, E2, E1. This is a product of all these matrices, and Q is a product of F1, F2 up to Fs. So since all these EIs and Fjs are non-singular, as these are your elementary matrices, so therefore P and Q are non-singular. So we have reached from here to here. So thus there exists a non-singular matrix P, let's say of order m, and non-singular matrix Q of order n, such that B is equal to PAQ, right? Proved? Okay. Now we move on to third part. From second part to third part. What is given in the second part? That suppose there exist non-singular matrices P and Q of order m and n respectively, such that B is equal to PAQ. This is given to us. We have to get that A is row equivalent to C and C is column equivalent to B. Now if B is equal to PAQ, let PA is taken to be as C. So let C is equal to PA. Now P is your non-singular matrix, right? And it is pre-multiplied with A. So can I write, therefore, we have obtained the C matrix by applying the row operations on A. So A is row equivalent to C. That is what we are saying, that A is row equivalent to C, right? Please remember, pre-multiplication by an elementary matrix corresponds to the elementary row operations. That is, I have written that C is obtained from A by applying the row operations, because this corresponds to the elementary row operations, the pre-multiplication of elementary matrix, right? Similarly, post-multiplication of an elementary matrix corresponds to the elementary column operations. So C equal to PA. So therefore, A is row equivalent to C. Reason, as P is non-singular matrix. This is your result also. Please take this as your remark also. Now since it is given that B is equal to PAQ, right? And this is CQ, we have taken PA to be C. So B is equal to CQ. Because Q is your non-singular matrix, so post multiplication of an elementary matrix corresponds to the elementary column operations. So from here we can write that this implies B is obtained from C by applying the column operations. Reason, as Q is non-singular matrix. So this is also result. Please take this as your remark. So from B is equal to PAQ, we have reached the third statement that A is row equivalent to C and C is column equivalent to B. And now to move on from third part to the first part. Third part is, suppose there exists a matrix C such that A is row equivalent to C and C is column equivalent to B. This is your third part and we have to get the first part, that is A is row column equivalent to B. We have to reach over here. Now if A is row equivalent to C and C is column equivalent to B, then there exist elementary matrices, let's say E1, E2 up to ER, and F1, F2, F3 up to Fs, such that because C is obtained from A by applying the row operations, so C is equal to, for elementary row matrices, we are taking this pre-multiplication of these elementary matrices to A. B is taken to be the post multiplication of these elementary matrices with A. Please remember, for the pre-multiplication, start from ER to E1. Take the product as it is. For the post multiplication, you have to start the product from F1, F2 up to so on up to Fs, right? So B is equal to C, F1, F2 up to Fs. Writing the value of C from here. So what does this implies? This implies that this B is obtained from A by applying the row column operations, right? Hence the result. So we have proved that all these three statements are equivalent, right? Okay, thank you.